for questions, okay? So I'll tell you, I'll give you, I'll let you know when you have to stop, basically.
Okay.
I'll try to time it. So let me put my meter on stopwatch. Timer, 10 minutes. Very good. So this is going to be almost APS-like.
Yes.
And then all of the participants are muted, right? Except the speakers.
Well, there is something pretty annoying that every time someone enters in the room, I see something popping up in my screen. But
that's right. So
can I stop that?
Elena, can you make me co-host so that I can mute everybody except the speaker?
Yes, okay. Okay, you are the host now.
Okay. Am I? I don't see myself as host. Elena, I'm not a host.
No. Yes. Yeah.
At least I don't have power to mute people. I see people are coming in. So please, everybody, mute yourself when you come in.
Oh, okay. Yes. Sorry. Okay. Now you're, yeah? Okay, now you're the host.
Yeah, so I'm admitting everybody that is coming. If you can admit people that come in, and then I'm gonna mute everybody. And then I will, so Alejandro, I'm gonna unmute you.
Now you can hear me.
Yep.
Okay.
Okay, so I think it's a good time to get started. So welcome everyone to this hot topics session. We're gonna have 4 talks. Each talk is gonna be 10 minutes and there's gonna be 5 minutes for questions. So the first talk is gonna be given by Alejandro Gonzalez Tudela. So Alejandro, please go ahead.
So thanks for the introduction. So today, what I wanted to talk a little bit is how you can study also twisted bilayer systems using ultra-cold atoms, which is a recent work that I did together with Ignacio Cirac from MPQ. And as I will not have much time, so I will only give you a flavor of how we propose to do it and the possible motivations that we have to develop this kind of framework. So, I mean, the study of twisted bilayers, I mean, we all know it dates back from more than 10 years, but of course it exploded with these experiments here, the chairman, when they were observing for the first time this unconventional strongly correlated phenomena at the magic angle graphene. After that, it triggered a lot of experimental activities, both also theoretical, but still there are many, I would say, many open questions, and it's a very fascinating topic and an open area of research. I would say that also that despite the experimental success, twisted bilayer graphene also poses some challenges, some experimental and theoretical challenges. The first of them is, of course, is also the source of probably most of the interesting behavior, and it's the fact that this is a very, I mean, when you are doing the twisting, you are going into the strongly correlated regime where the tunneling in this effective Moiré supercell is of the order of the electron interactions, and this makes that well-known methods to study this system based on perturbative treatments or or similar, so they do not work. So that's one thing. The other thing is that due to the small angles where this magic angle behavior happen, so the size of these moire primitive cells are huge, which complicates a lot. First, let's say theoretical description based on ab initio calculations, but also, like say, from the experimental point of view. So I guess it makes this order very important, and we also in the last talk. So this is also another source of complication from both theoretically and experimentally. Also, something that I find, and it was mainly motivated my my research in the topic, is that although you can do many things in the twisted bilayer graphene, like magnetic field, temperature, and so on, there are some other parameters, like, I mean, the ones that have to do, for example, with the interlayer hopping or the intralayer one, so are kind of fixed by the material. So there is not much that you can do around it. So because of or partly because of this limitation, I think that there are still a lot of open questions, and there is a lot of research trying to understand the whole phase diagram in these experiments. But now you have kind of, I would say, two roads that you can take to increase understanding. One is this path of trying to improve existing samples, develop new measurement techniques so that you can learn more things from the material. And we have seen several talks already where this is really going quite fast, so it's really improving a lot. But the other one that I would like to convey in this talk is that maybe you can also build synthetic systems. Maybe they don't reproduce the whole behavior of twisted bilayers, but you can get some of the features. You can try to learn something from these synthetic systems, and then maybe you can take the knowledge back to the solid state realizations. And in particular, what we propose is to use these ultra cold atom systems that have been already very successful to explore other kind of condensed matter problems. As maybe in the audience, there is some people that is not so familiar with ultra cold atoms. Let me give a brief crash course on these ultra cold atom systems. I mean, ultra cold atoms are just based in optical lattices, are created by sending content propagating lasers in free space. And then these atoms interfere, these lasers interfere, and they create trapping minima for the atoms that can now hop from one side to the other, creating some tunable hoppings that you can control with the laser intensity or the tuning of these lasers. You can also control the way these atoms interact when they are sitting on top of each other in lattice minima. And also by controlling the laser configuration, you can tune also the geometry. And in fact, I like to highlight here that artificial graphene has already been created in these ultra cold atom systems, like the individual layer graphene, if you want to say, in this experiment by Leticia, who is now also at Icfo. So what we would like to do now is, I mean, of course, proposing a way of simulating the bilayers. And sorry. And the key asset that we will try to harness is the fact that in ultra cold atoms, you typically don't have a single ground state, but you have many, because, for example, the nuclear spin is coupled to the electronic one, and you have hyperfine multiplets that can be used as internal atomic levels. And in particular, we want to use what people call these state-dependent optical lattices. And it's the fact that in certain conditions, you can engineer independent, well, almost independent optical potentials for these two internal atomic states, that what we would like is that each of them will play the role of a layer. And then the advantage is that these two states can be connected optically through a microwave transition and simulate the interlayer hopping between the two. So like this, actually, the main advantage or my main motivation when I was starting this field is what will happen now if you have a system where you can increase a lot the interlayer hopping. As you see here, I will consider during most of the talk, except in some last part, square lattices, because you will see that some of the features that appear in twisted bilayer graphene are also present here. So you can start learning things from these square bilayers. So let's see how we do it. So the way we plan to do it, and we propose to do it, is using these alkaline earth atoms. So alkaline earth atoms are these atoms, it's the second column in the periodic table. And they are characterized by having 2 electrons in an outer shell, and they give rise to a very interesting level structure, which in particular, for what is relevant for this talk, is that they have an optically excited state, which is metastable because it has a double spin forbidden transition to the ground state. So it has a very long lifetime. And in particular, you can harness it as if it was an atomic internal level, so you can live for long enough. Then also, then you have this feature, plus the fact that when you have a fermionic isotope of this alkaline Earth, so you can have non-zero nuclear spins, and these clock states, this ground and excited state, are split in also magnetic hyperfine multiplets that you can also harness to engineer these bilayer potentials. So in this paper, we propose several ways. I only give you a flavor of two of them. I mean, one of them is basically harnessing these multiplets that appear, these non-zero nuclear spins, when you add a magnetic field. And then what we do is actually creating the twisting by just twisting the mirrors that we can put when you send a laser from here, you twist it, and you add a halfway plate so that the polarization of the paths here in red is orthogonal to the ones in blue. And this the magnetic field basically allows you to create almost independent potentials between the two, and that give rise to this twisted bilayer behavior. So sorry that I cannot explain more because I don't have the time. Also, another option is a more brute force is to use the ground, these two clock states as the two layers for the bilayer. And the idea is that actually there is some certain wavelengths in which the laser create completely independent potentials for the two. So they are called tune-out wavelengths. And the only potential problem is that the periodicities, because the wavelengths are different, the periodicities of the two bilayers will be different, but you can correct it by making some angle when you create the angle in the out of plane direction to correct it. So these are the two ways. So let me illustrate now what kind of physics emerges from this, for example, for these square bilayers. And to make the calculations, it will be mostly band structure calculations and density of states. I will make some brute force simplifications. So I will assume that I only have nearest neighbor intralayer hopping, and that the interlayer hopping is only local. So only when they sit on top of each other, the atoms are being able to exchange interactions between the two. So this is, for example, a figure that illustrates this physics that I wanted to explore with this phenomenon. So what I'm doing here, I'm making a twisted bilayer pattern in which I put the first commensuration angle where these things behave like a Maré pattern. So this is, for example, here the reds and the blue dots are the upper and the lower layer. This will be the unit cell. And what I'm plotting is the density of states as a function of the interlayer and intralayer hopping. And you see that as you increase the interlayer hopping for fixed angle, you see that the speed of the singularities. You also see that at the upper and the lower part of the spectrum, that some bands are isolated. Also, we explore a little bit what happens as you start decreasing the angle, and you recover this narrowing of the density of the bands as you are making the angles smaller and smaller while keeping the interlayer hopping fixed. And all these things can be understood from the projected band structure. And here I just wanted to highlight that there are also a lot of this, what it was named in this paper here as higher order Van Hoff singularities that can be explained from the different degeneracies appearing here in the projected band structure. It's just to get a feeling that with this kind of systems, you can get similar phenomenology. So we also made calculations with honeycomb lattices, and we also saw that also by fixing the angle, like pretty large angle, 21 degrees, you can also, by increasing the interlayer hopping, just isolate two bands around it and also make them closer to the original Dirac point. And you see that this is an interesting route. I mean, maybe it can provide a way to observe this strongly correlated phenomena of flat band physics, maybe with larger angles, and can help to discuss certain mechanisms. Like, for example, here we will not have problems of structural relaxation or phonons. So you can discuss certain mechanisms that are thought that are related to this phenomena appearing here. Also, I wanted to put here that you can maybe find new ways of probing the system. So we explore, I mean, a way of doing it by coupling kind of quantum emitters. It will be like putting a localized tip and finding an emission excitation into these bilayers, and you will find some non-trivial features in the emission. And also, I would like to make some connection with some proposal that we did recently to simulate quantum chemistry problems, and to export it here to also investigate the role of local versus non-local interactions in this twisted bilayer graphene. Maybe I don't have the time to explain it. Okay, so that's, I think it's more or less almost the time. So, I mean, just to say that, I mean, these synthetic twisted bilayers can be obtained using these state-dependent traps with alkaline earth atoms. I think that they can be a complementary platform to study twistronics, maybe providing access to a novel parameter regime and novel ways of probing. There is also a recent related work that I think is the last talk of this session that they also propose a different way using synthetic dimensions, so they don't really do a twisting of the potential, so it's through some Raman-assisted transition. And with that, I just wanted to acknowledge Ignacio again, and thank you for your attention.
Thank you very much, Alejandro. So we have a little bit of time for questions. If any of you can unmute yourself and you can ask a question. I believe you're able to unmute yourself. Let me see. Yep.
I have a question.
Sure, go ahead.
So can you simulate non-local interactions which appear in twisted bilayer graphene due to the overlap of near functions in your cold atomic proposals?
Yes, like this is what I was trying to explain here. So typically the interactions in cold atoms are local. So they only interact with the atoms are sitting on the same side. But motivated by a different problem, basically they're trying to simulate quantum chemistry problems. In this proposal here, we gave a method in which actually you can generate non-local interactions out of local ones. So it requires a little bit of complexity. You require to add an additional atom, so you need an atomic mixture that is used as a mediator of the interaction. But for example, in this paper here, you can read in the details, we were able to simulate 1/r interactions, like really Coulomb-like. So pretty long range interactions.
Yeah, but when you add some extra media to the system, it's not just the interaction transmitter, right? So you introduce some extra degree of freedom, which not necessarily just provides this particular consequence, right? So how you can control this? Could you elaborate?
You mean how can I control the shape of the interaction?
No. How you can control that it only modifies the shape of the interaction and does not modify anything else?
Well, I mean, they are pretty much independent, so they will only, I mean, this is pretty standard, I would say, in cold atoms. When you have atomic mixture, so you have some of them, if they are interacting, I mean, so of course it modifies things, but it only modifies because they are only able to interact this additional atomic species locally with this other atom. So it will not modify well, of course you have to make sure that you don't modify the optical potential that is creating the twisted bilayer. So well, there will be some working conditions that I still didn't work out. But I mean, given the proposal that we made here for the quantum chemistry, I'm pretty optimistic that this would be possible without modifying or distorting the behavior of the bilayer. So.
All right, thank you.
Okay, and we have time for maybe one more question.
I have one.
Sure.
Yes, Maciek.
So I think it's more a comment than a question. I think in all these atomic proposals, I think the focus is on the fact that you can control the interlayer coupling very strongly, which is very difficult in solid state. Mm-hmm. And this opens new ways to do not only bigger angles, but also new kind of physics, I think.
Yes.
Thank you.
Well, that was, yes.
Okay. Thank you very much.
My motivation, let's say, for this work. I mean, I saw a way of increasing the interlayer hopping because there is this somehow mindset that basically the fact that this angle, this magic angle appears at 1 degree is because the interlayer hopping in graphene is also small. So I thought, okay, maybe just by pushing a little bit, I can make it a larger angle. But as yes, as you say, maybe it's completely different physics as well. Yeah.
It's also the disorder of angle can be controlled here.
As well, yes, of course.
After talk of Eli Zeldov, we know it's very important.
Yeah, totally right. Yes, I agree.
Very good. So let's thank Alejandro again for his talk. And now we can move on to the second talk of the hot topic session. So this is by Niels Hesp. So Niels, if you can share your screen. Okay, very good. Go ahead. Nils, are you there? So let me unmute you.
He's muted.
Yeah, let me unmute you, Nils.
Okay, okay. Sorry.
All right, I think
Thank you,
you
Amy.
should be able to go now.
Okay. Thank you for enjoying this these online talks here. So we'd like to give you a short overview of what we have been doing in the lab here. We do near-field optical microscopy in the group of Frank Koppens at Icfo. And so on this, I would like to show mainly the experimental results that we have got. But on Friday, there will be Marco Polini talking about this this work and mainly focused on the theoretical part of it. So this has been done together with a group of Marco Polini, and we thank Pablo for all the samples that we got from him, and also the collaboration with Kachias for the theory. So this near-field optical microscopy is a tool that allows us to measure the optical conductivity at a scale beyond the diffraction limited. So in this case, it's limited to about 20 nanometers, depending on how sharp your tip is. So what we do, we have a very sharp AFM tip that is metallized, and we can focus an infrared beam on top of this. And because the tip is metallized, this will create a hotspot of light right underneath the tip. And if we scan over our sample, we can measure locally the optical conductivity. In addition to this, because this tip is so sharp, it can provide momentum to launch plasmonic excitations, and also used to visualize them. So what we do in this work here, we measure collective excitations in twisted bilayer graphene close to the magic angle. So with this tool here, we probe interband plasmons and twisted bilayer graphene. And so the scheme is that with these interband plasmons, we can determine the dispersion of them. And this is related to its optical conductivity. And this in turn, we can relate to the band structure of bilayer graphene. And by comparing it with our results, we can make conclusions about the tunneling constants in the AA and the AB regions in this system. So most of the results I will show are the device slightly above magic angle, but in principle it's for angles around magic angle, all valid. So typically, so this is what a typical device looks like. An optical image is rather small. It's a hall bar which is used for transport measurements, and a group of Pablo. And so what we do, if we zoom in here, typically you don't see much in an optical microscope. But now with our near-field microscope, we can scan over this and see beyond this what the optical conductivity looks like. And this is what we observe. So it's not like an homogeneous system inside here, but we see what we call patches of optical activity surrounded in the sample. And inside these areas, you can observe sort of oscillations. And we think these oscillations are interband plasmons that are being launched by the AFM tip at a certain position, and then get reflected, bounce back by these edges of these cavities, and then couple out via the tip to the detector. So this is for a certain excitation energy in the infrared. So what we do, if we vary the excitation energy, so the energy of this interband transition, you will see that the patterns, so in particular the wavelength of these oscillations changes. So it becomes larger for lower energy, meaning the wave factor becomes smaller for lower energy. So we interpret this as follows. So if this is a typical band structure that people look at, the transport experiments focus on these flat bands here because you cannot dope too much. However, with optics, you can excite these interband transitions from these flat bands to the first excited state. And this is the typical energy scale we look at, an order of 100 to 200 millielectron volts. So this is where our optical microscope comes in. And what we do in the experiment to determine the dispersion of these plasmonic excitations, so we scan on one of these lines. So we stay fixed in position, scanning along this line, and vary the excitation energy while scanning. And so here we see these plasmonic excitations changing its wavelength, so changing its momentum. So we can extract the momentum from this. That's what you see here, the plasmon wave vector increasing, so shorter wavelength for higher energies. And this in turn, we can correlate with the resonance condition of a plasmonic excitation. So this correlates to its optical conductivity, to the plasmon wave vector. So from this, we deduce what the optical conductivity should be. And this is something what we can calculate from theory. So what you see here, there are two fits. One of them is the Drude conductivity, which is this steep line, which is typically present for plasmonic excitations in single layer graphene. However, this is a interband plasmon, and therefore there's an offset in energy, something like around 200 millielectron volts, and that gives this much steeper profile. So if we compare this with these band structure calculations that people normally look at, so the Cochino model is a typical model. It has two main important parameters, the interlayer couplings at the AA regions and at the AB regions, typically in these magnitudes. And from this you also get interband plasmonic excitations, we calculated using the Kubo formula. But since the bands are not very parallel to each other, it gives kind of a weak resonance and the optical conductivity. And here are our experimental data points. So now what we can do, we can adopt the model pioneered by Vishwanath, which puts the AA interlayer coupling to 0 millielectron volts. And this is a so-called chirally symmetric continuum model. And in this case, you get much stronger band nesting, meaning that these bands are much more parallel to each other. And of course, this gives a much stronger resonance and the optical absorption. And this in turn can give rise to plasmonic excitations at these energies. And this is what you see here. So the experimental data compared to the theoretical calculations using this model. So this suggests, our results suggest that there's a strong suppression of the interlayer tunneling in the AA regions, this U0 parameter, which goes together with stronger band nesting and has its influences on the in the strong correlations in these systems. And the nice thing about this is that these experiments are done all at room temperature, so it's a rather easy way of accessing these type of parameters of the system. So on Friday, Marco Polini will give much more details about this, in particular about the theory. So for now, I would like to show something else, which is also related to twisted bilayer graphene, and that's near-field photocurve mapping. So it's a different technique. The idea is rather similar. So you have a metallized tip, and in this case, we focus light on it, but this heats up the electron gas, and because of the photothermoelectric effect, you can induce a current. So while scanning over our twisted bilayer graphene sample, we measure the current between these electrodes. And in this case, we do this with a sample which has twisted bilayer graphene with a near zero twist angle. So you would expect lattice relaxation and domain formation. So this is what we observe using this photocurrent mapping technique. And we see these regions, these patches in the twisted bilayer graphene region of these positive and negative photocurrent areas, and they correspond to the lattice relaxation in this system here. So the domains are kind of in a square lattice with the diagonals in between, which are kind of hidden because of the contact geometry. So the way we understand this is as follows. So you have the AB and the BA regions, and intermediately in between you have the saddle point. So these are the domain walls. So this forms a grid, and since the conductivity is different for these saddle points, or for the domain walls, also the Seebeck coefficient is different. So you can imagine there's kind of a delta function in each of these domains. And if we kind of create a grid like this and impose on this the photothermoelectric effect, which means that if you have heat locally generated with changes of the Seebeck coefficients, you generate a photocurrent, you would predict to observe a photocurrent pattern which looks like this, and this is also what we observe here. And this shows that this is a very nice tool for the local relaxation, for mapping out the local relaxation of twisted bilayer graphene. And this is not only limited to near zero angles, but if the resolution is good enough and if the twist angles are small enough, we can also observe it in those cases. But of course, the next step in experiments will be to utilize these domains along here and open a gap in the system by a perpendicular electric field. And in that case, you have these topological quantized states at these domains. And of course, it's very interesting to do physics with that. So with these two topics, I would like to thank you for your attention.
Okay, thank you very much, Niels. So now we have a few minutes for questions. Please unmute yourself and ask a question.
So I have a question.
Andre, go ahead.
So I'm sorry, what was the claim about the chiral limit? You're claiming the data is very consistent to the chiral limit?
Yes, at least, so our claim is that...
but which chiral, like if I change the U1 parameter, then those bands also change. The chiral limit is not only U0, it's also U1. So why would you leave U1? There's a full parameter, there's two parameter family, right? There's U0 and U1. So I'm just like slightly confused why you're just focused on U0 equals 0 and U1, you keep it the same value. I mean, how do you know there's no other, it's a two parameter family of U0 and U1 values, and you just keep the same, value.
So we have scanned both of them actually in the calculations, and the most pronounced effect is for the U0 parameter only, while the U1's parameter actually doesn't change so much in these cases. I think, remember.
But we know from the gaps versus bandwidth that it's not really. It can't be really in the U0 equals to 0 limit, right?
No, true. No, so actually this is kind of extreme illustration that we put here for the case of when it's exactly 0. But if we do a continuous sweep of this, we actually see the value close to our experiments is something near 40 millielectron volts. So like half the value people typically tend to use in the other model. So okay, it's kind of illustration that the bands are
zero interactions, because interactions can also flatten the bands and give you the impression that you're more in the chiral limit. But this is computed with 0 interactions.
Yeah, in this case, yeah.
Okay.
Yeah, but actually the optimal, so in one case, I mean, this is not a fit in this case here, there's an overlap of data, but the other parameter we can compare is just the energy, so the energy difference between these bands here. And in that case, the match is best for an intermediate U0 value, around 40 millielectron volts. So the position of this absorption peak.
I see. Okay, so it's 40. Okay, good.
Yeah.
Thanks.
Okay, are there more questions? Maybe Niels, you could clarify the conditions for the experiment. Is that actually room temperature measurements, etc., and
yes.
ungated samples, and yeah.
Yeah, so in this case, what we did, we used the samples from Pablo's group, which were characterized at low temperatures to determine the twist angle and also whether or not they were superconductive. But all these experiments afterwards are done are at room temperature in this near field microscope. And in principle, the condition for these interband plasmons is not depending on the temperature. But of course, the interesting part will come when we cool down the sample in the cryogenic near field microscope. We hope to do this very soon, and then we will be able to go down to this, at least to the correlated insulator regime, and hope to see, well, interesting phenomena over there.
Very good. Is there any other question?
Do you hear me?
Yep.
So you said these devices were characterized at low temperature. So did you see any superconductivity before you do this experiment?
So this device was slightly above superconduct for the condition of that, so 1.35 degrees. But we have seen this in various devices, which are all around magic angle. And in that sense, it's not surprising because flat bands are, of course, the flattest near magic angle. But what matters for us is the joint density of states. So you want both of the flat band and the first excited state both to be rather flat to have a strong interband excitation. And this happens for, well, a range of angles between 1 and, let's say, 1.8 degrees. Thank you.
Very good. So the time's up. Thank you very much, Niels. And we're going to move on to the next hot topic talk. So if Shabo, you can share your screen and unmute yourself. Yeah.
Share screen.
Yeah.
Whatever. Where can I share?
There's a button to share.
Yeah, I found it. I found it. Yeah. All right.
Very good. Make it full screen and then.
Yes. Thanks, Pablo.
Very good.
Thanks a lot. Yeah, my name is Xiaobolo, and I'm a postdoc working with the Dmitriev now. So yeah, I'm local here. So I just quick show some fancy stuff around Icfo in Barcelona. So hopefully, in short time, we can have some on-site conference, and then you can check it out yourself if you are interested. So today, I will talk about some fragile topology in twisted bilayer graphene and how it is reflected on its Hofstadter spectrum. So at first, I would like to acknowledge my collaborators, especially Dmitriev, who is leading the experiment. And for the theory side, it's done by Bill, Andre, Gareth, and Alan. And also we get some strong support from some other groups, like Martino's group from Basel, Benjamin's group in Grenoble, and the Japanese group who gives us very nice bilateral crystals. Since Andre already gave very strong and detailed introduction of the band topology, here I just maybe highlight some key points here. We know for some trio bands, the intrinsic features is that it can be represented by some localized Wannier orbitals in its atomic limits. So actually it is quite different in non-trivial band or a topological band. So basically we cannot find any localized symmetric Wannier functions to describe this system. So later people found that even inside of this group, there are still different scenarios. For example, for some topological band, if we further add some trio band, actually the topological features are still robust. And for some other topological bands, actually it can be further trivialized by adding some other trivial sources. Basically, it comes to the concept of fragile topology, which has been predicted by Ashwin's group maybe a few years ago. So here, later people found that the signature of fragile topology is some acoustic metamaterials. So I'm not go into details of this work, but it's published in Science early in this year. So basically, they build this kind of lattice, and then they calculate. They also measure the spectrum of this kind of metamaterial by comparing the localized orbitals in atomic limit. They found that it's not possible to represent it by the localized orbitals. And this gives the topological features, and it can be further trivialized by adding some other trivial elements. So here comes the question, do we have some similar fragile topology in crystalline materials? So actually, as Andre already talked earlier today, in twisted bilayer graphene, actually it carries the same similar fragile topology. So we know for twisted bilayer graphene, the difference between the two intrinsic graphene brilliance gives the two decoupled Murray Branzo. Inside of each Murray Branzo, actually the lowest two miniband are connected by two direct points. So the interesting thing is, if you look at the helicity of the two direct points, actually they are the same in the same valley. So this actually is in very sharp contrast with the monolayer graphene. You know, in monolayer graphene, the direct helicity of in two valleys is opposite. Basically, in monolayer graphene, the total helicity is 0. However, here for twisted bilayer graphene, the lowest two miniband just gives the non-zero total helicity. Basically, it indicates the topological features or the fragile topological features of the twisted bilayer graphene. So now we may ask, will this kind of fragile topology give any physical effects which can be observed in experiments? So actually, Andrew already showed in his talk earlier today, it can be reflected on the Hofstadter spectrum. So just take an example of the two-band model. So if you just look at for example, this is two trio bands which are gapped by, which are separated by a band gap. Actually, if you look at the Hofstadter spectrum, each band give a Hofstadter spectrum, but the two Hofstadter spectrums are just separated by the band gap. That means the two sets of Hofstadter butterfly will not talk to each other. But it will be quite different if you look at the topological band. So here we just took the two chain bands, for example. So the two bands are separated by a chain number 1 gap. However, the Hofstadter butterfly here is quite different with the trio case. So the Hofstadter butterfly of each band will not be bounded by itself anymore here. So later, Bill and Andrew also figured out that actually twisted bilayer graphene, the fragile topology will also give the similar unbounded Hofstadter butterfly. For example, here, this gap will be interrupted by the 4-0 lambda level gap. So the 4-0 lambda level gap is the chain number, the total 4 is the total chain number, considering the spin and valley. And so this 0-1 gap is the gap between the flat band and the dispersive band. So then we observe the Hofstadter butterfly at lower magnetic field. We design this kind of samples at lower twist angle. So we managed to observe all the minibands, at least the lowest 8 minibands, which are well separated with each other or connected with the direct points. So as Andrew showed today, actually the lowest 2 minibands are connected by 2 direct points, and they carry the same helicity and giving the fragile topology. So then we measured the Hofstadter butterfly to 16 Tesla, which corresponds to about 3 quantum flux through Murray cell. We found that some lambda level gap originally from charge neutrality just across a few minibands, which gives the unbounded Hofstadter butterfly. It is just like the topological case. Here we zoom in this region. We can see this gap is from the charge neutrality, and it clearly interrupts the first miniband and the second miniband, and basically it connects all these Hofstadter spectrum together. So we also calculate the Hofstadter spectrum, which can perfectly match our experiments. So basically this 4-0 gap is this one, and also it can interrupt by the second midband and the first midband here. So we can also resolve some other connected features in this both in experiments and the calculation. For example, here the first midband can be also interrupted by some other lambda levels originating from the -1 midband here. So I think it's down here. Thanks.
Okay, thank you very much, Shabo. So we have time for a few questions. Anyone, if you want to ask a question, please unmute yourself and ask.
Hello, Shabo. Thank you very much for the presentation. It's really interesting data. And I realized that in your transport curve, at full filling, the resistance of the sample is lower than at half filling. Yeah, that's the slide 16 and 17.
Slide, this one?
Yes, exactly. So at full filling, the resistance is lower than at half filling, right?
So actually here, so basically this is different miniband. It's different with the first magic angle. For first magic angle, we have a full filling. So basically here, this is the first miniband, here's the second miniband. So this is all single particle picture, no correlation.
Okay. Okay, now I understand, thank you. Okay, so
because, here, I think in the second magic angle, because the Murray wavelength is larger than the first magic angle, and you know the correlation, the electron-electron interactions may be weaker than first magic angle. That's why we didn't observe the correlated features.
Oh yes, okay. Thank you for the clarification.
Hi, Shabo. I'm wondering if your experiment in the Hofstadter spectrum is sensitive to whether this is fragile topology in particular, or just that you have valley selective Chern numbers. Is that a meaningful distinction? My understanding is that it's related to whether you have C2T symmetry preserved or broken.
Exactly. So first, the fragile topology is protected by the C2T symmetry, and then actually the connected features of the Hofstadter is because of the fragile topology of the lowest 2 miniband.
So in twisted double bilayer graphene, for instance, you don't have fragile topology, you don't have C2T symmetry, but you still see these interruptions in the single particle gaps in the Hofstadter spectrum. So I guess I'm asking, can you tell from the Hofstadter spectrum whether you have in particular fragile topology, or just that you have valley Chern numbers that are not zero?
I'm not 100% sure about the twisted double bilayer graphene. At least I haven't seen any theory about the fragile topology in twisted double bilayer graphene. But the difference is that the fragile topology in twisted bilayer graphene comes from the non-zero total helicity, which comes from the 2 Dirac points connecting the lowest 2 milliband. I think this is different from the twisted double bilayer graphene, right?
Maybe if I could ask just one more quick follow-up. So if you were to align the system with boron nitride, you would break the C2T symmetry. And in principle, you would lose the fragile topology, but you would still have the non-zero Chern numbers of the bands. And in principle, you would still see these interruptions in the Hofstadter spectrum.
Actually, the non-zero Chern gap is it's lambda level gap. It's not the intrinsic. It's not like the stable topology. It's just lambda level gap.
Maybe I can comment a little bit on the theory.
Yeah, please, Andrew.
This is the more theoretical question, really.
Thanks, actually.
So you're right. If I put boron nitride, I would get, so this doesn't have value chair numbers, right? Because it's got basically, if I don't put boron nitride, if I put boron nitride, I would get value chair numbers, as you say, and then the gap at 0. So considering no ferromagnetism, then the gap at 0 would vanish, which is what happens in the twisted double bilayer. Here is the gap between the basically, the gap that's getting interrupted is the gap between the active bands and the passive bands. If I would have boron nitride, I would open a gap at charge neutrality, and I would, and then because it would have, as you said, very selective Chern numbers, that gap would vanish, like in the twisted double bilayer. So there are really two different types of topology. So basically, what this is telling you is that you do have some sort of topology. You know, based on the symmetry of the systems, it's fragile, but you know, you wouldn't be able to completely say it's fragile. Like you wouldn't be able in twisted double bilayer to say it's completely valid Chern numbers. You just would know that it's some type of topology. If you had mirror Chern numbers, it would look the same in twisted double bilayer, for example. You'd close that gap too. So these things tell you that you have topology based on the symmetries. The topology is fragile in this case, and it's valid Chern number. But you need, you know, you can't expect to get everything to completely characterize the full topology by such a sharp measurement, right? That's kind of like it's a one type measurement, right? Gap closing or gap not closing, if that helps.
Sorry. Yeah, no, that's helpful. Thank you.
Sure, thank you.
Okay, thank you everyone, and thank you, Shavo. So we have to move to the next talk, next hot topic talk. It's going to be given by Debraj Rakshit. So Debraj, if you can please share your screen and unmute yourself.
Yes, thank you. So thank you for this fantastic opportunity for presenting our work. And so we'll talk about an ultra-cold simulator for implementing twistronics, but without a real physical twist. So for this may seem a bit puzzling at first, but hopefully by the end of our talk, we will be able to convince you that about the underlying idea. Okay, so this paper is based on this work that's currently in archive, but in production in PRL. So if you are interested, then you can look into the archive version, and has been done in collaboration with fantastic collaborators, Timek, Alessio, Ravi, Irene, Leticia, and obviously Maciek, in whose group I am working as a postdoc. So I will explain these things very hand-waving way, because we don't have a lot of time. First, if we want to motivate that why do we really care about this simulator? And Alejandro in his talk actually did this job very fantastic way, but I will say in few words. So this bilayer materials are obviously endowed with strongly correlated phenomena, which are very exotic. Okay, and culmination of which obviously happens in the magic angle graphene, right? And you get sort of fascinating properties like correlated insulating phase, superconductivity, and there are topological aspects and things like that. But also there are also a lot of theoretical efforts to understand their underlying mechanism, and that brings a lot of debates and doubts. So what I think that if we could build a simulator which could mimic at least the essence of twistronics, then we will have this advantage that we can manipulate these parameters very flexibly and with high precision. And most probably that could help us identifying these key microscopic ingredients behind the origin of this strongly correlated phenomenology. So this is the motivation. And obviously, why we can be optimistic with this ultra-cold simulator, because this has already reached a very advanced stage, and with all sort of tabletop experiments that happened for realizing different sort of interesting condensed matter model systems like Bose-Hubbard, Fermi-Hubbard, spin chains, or even Halden model, for example. Okay. So here I will explain the precursor of the idea actually. So we can obviously create two optical lattices and then try to directly twisting them. And this was the first actually talk by Alejandro. And this is very nice approach. But when we are first planning to do and thinking about doing a simulator, we thought of two immediate challenges that the experimentalists could face. First of all, this optical lattice through if you directly rotate them. So this is a bit involved process, and then okay, there can be certain challenges in stabilizing the platforms. Okay. Secondly, our samples are intrinsically mesoscopic. Okay, so it's really difficult to create these large lattices with large supercells. Okay, so which happens in a magic angle, right? So it has something like 10,000 lattice sites. So in ultra-cold atoms, this physical distance between two atoms is of the order of microns, 10 to the minus 6 meter. In compared to 10 to the minus 9 in magic angle graphene, something like that. So this is an obvious challenge. So we cannot create in principle those huge supercells. So then we thought that we have to think something of a different idea. And this idea that if you, when you really do a physical twist, what happens? That your interlayer coupling gets spatially modulated, right? So it's like for different twist angle, you will get a different pattern of this interlayer spatial modulation. Okay, so in condensed matter, so now we can think of doing something, okay, where we will not actually physically rotate our optical lattices, but we will directly take some technique from the toolbox of a cold atom and do these spatial modulations, which will help us create these units, large units, large supercells, the way we want, and the more pattern, in fact. Okay, so this is the underlying idea. And on condensed matter physics, it's more closely like if you have two lattices, and then you are giving different pressures at different points, you can create this kind of modulation, right, without twisting. Okay. So with this idea, then I would like to mention that our idea is really not to do a one-to-one correspondence with what's happening in magic angle graphene, but still we'll show that through a very simple construction of a square lattice and a simple modulation of this interlayer tunneling, that we can actually get a band structure for magic configurations which shares many features with this twisted bilayer graphene. Okay, but importantly, we have a very small supercell, and our construction will show that it can support a non-trivial topology. So, so here, this is the work is based on two key ideas. Okay, one is this, as I said, the spatial dependence interlayer tunneling. That is spatial dependent Raman coupling that I will explain a bit more in my next slide. And then there is another idea, which is synthetic gauge field in synthetic dimension. Okay. So, so this slide more or less sketches the schematics of our proposal. So on left hand, you can see that there are two layers, and these two layers are created by two internal states of neutral atoms. Okay, and then we can couple them by lights. This, when we couple these internal layers by light, this creates an induced tunneling. Okay, this so this is our synthetic tunneling. And the gauge field comes because from the there is a recoil momentum from the Raman light, and this recoil momentum will give you a pale space, which is shown by this gamma. Okay, and so and each of this placket will have a non-zero flux actually. So, and then what kind of atoms we really want to do these experiments? It's this alkali-earth atoms, and we pitch in this strontium and ytterbium, because they have a large nuclear spin manifold, which can be precisely controlled in experiments. And more importantly, they are SU and invariant interactions. That means there is no collisional distribution between different spins. Okay. And to elaborate it a bit more, let's look into this figure into the right. Right. So while we have this optical lattices are created by this counter propagating laser beams, so that will create our square lattice. Then we will have this Raman, which is aligned at some angle with respect to the plane. Okay, and then this angle can be tuned the way you want, and that will actually control the magnetic flux. Okay, and so now in this lower there is this internal levels are shown, and you will see two different colors, the orange and the green, and these orange levels will signify one of the layer, and the green is for another layer, and these two layers can be actually coupled by these two photon Raman transition. And then there is a detuning parameter, okay, delta 0, and this detuning parameter can be controlled, and your strength of the Raman coupling depends on this detuning parameters. It's exactly inversely proportional to this detuning parameters. So controlling these detuning parameters, you can play with the strength of the synthetic coupling. Okay, and how do we create this modulation? So for that we use an additional laser and excited to excited state transition from 3p1 to 3s1, and this actually creates a large light shift in this 3p1. As a result, this result of this light shift, this detuning parameter delta 0 gets modulated in space, and resulting in a space dependent tunneling omega spatially dependent tunneling omega xy. So this is the Hamiltonian, where we have this tunneling term, physical tunneling term, and this synthetic tunneling term with the phase. Okay, so this is our very simple system, and now we can play. Now we can control the supercell dimension by just changing Lx and this periodicity, Lx and Ly, which can be controlled in experiment. Okay, and so now if you do this, then you'll see this actually has a symmetry around E equal to 0, the energies. Okay, so I will concentrate only on the negative energies because it's exactly symmetric. And then this band manifold, if you look into, then it has for Lx into Ly, for the periodicities, you would get this particular band structure, and that we call magic configuration. So, so whenever Lx equal to Ly equal to 4 nu, where nu is integer, this kind of band structures appear. Okay, and these two middle bands in between, they are quasi-flat, and the flatness of this can be controlled precisely. Okay, by tuning the strength of this Raman coupling, and also this dispersive band in close proximity, and they are Dirac bands, and this velocity of the Dirac bands can be also controlled by this by tuning the flux of the magnetic flux that we introduced before. Okay, and you can see that this kind of shares some features with this magic angle graphene that is shown on the left. This is a paper from the McDonald, but most probably I forgot to cite it. And for example, you can set the criteria by different criteria. For example, you can tell that this is a vanishing Dirac velocity and maximum band gap to nearing bands, or narrow bandwidth with respect to the bandwidth of the neighboring bands. And we know this particular band structures are precursor to many interesting strongly correlated phenomena that's happening in the lattices. Okay, so we can separately actually satisfy these conditions. So using these controllable parameters over wide ranges like Raman coupling, magnetic flux, supercell configuration, inter-layer atom-atom interactions, we have large flexibility. But you will see these bands are actually touching each other. They are really not isolated. So if you really want to open a hard gap, then you need to do some additional mechanisms, and we can do it by staggered next nearest neighbor complex hopping or lattice dimerization schemes. Okay, I will not explain that because them in details because I don't have time. But then doing that, you can also look into topology, and you can actually play between different topological phases by tuning the parameters, for example, by introducing a chemical potential, and you will get completely trivial band, for example, or you can get standard non-trivial, which is like this dispersive bands have non-trivial Chern number, and this middle band has 0 Chern number, or standard non-trivial, or it occurs after a phase transition that this Chern number switches, and then this middle band becomes a non-trivial Chern number. And this Chern number is a topological invariant and remains constant as long as band gaps are preserved. And we'll actually put a paper next week with a lot of extension of our proposed scheme and with main focus on topology. So if you are interested, then you can look into that. For future, okay, there are many future proposals, but to be simple, that we can explore different lattice structures. For example, in Honeycomb, if you do, it will give us this Dirac cones for free, and then we can play with that. Okay, and also we can impose other spatial modulation patterns. Okay. And also, we want to do strong correlation effect through tensor network or things like that. So these are for the future. Thank you very much.
Okay, thank you very much. So we have a couple minutes for questions. If anyone would like to ask, please unmute yourself. Any questions? Please unmute yourself. So maybe
I have a question.
yeah, sorry, go ahead.
I have a question about the use of Raman. In the diagram you show something like the 1x level for the layer 1 and layer 2 are different in energy. I wonder why. In this picture, you can see that you have a green level 1x for one layer and another energy level for the other layer. I wonder why you have that. I expect that both layers have the same energy initially.
Yes.
So I wonder.
Because we are using this optical lattice trapping potential, which is basically spin independent that we propose. So for in principle can have the same energy, but they can be coupled by different strength. For example, omega 1 and omega 2, and this then this. So then your Raman coupling transition strength will be omega 1, omega 2 by delta 0. So for showing two different omega 1 and omega 2, most probably do it like that.
Okay, thank you.
Okay, we are now already at 15 minutes, but if there's any quick question, we can ask. Otherwise, we thank speaker again. Is there any question? No? Okay, so let's thank Devraj again, and as well as all of the speakers for a very interesting hot topics session. And we hope to see you later at the town hall or tomorrow again for the next 2 talks. Thank you very much, everybody.
Thank you.
Thank you.
Thank you.